let's now look at another example where we are going to say that we are going to use a no bias neuron. And what it means is that we are simply going to say that the bias is 0, which means that the decision boundary is going to pass through the origin. Right? So if we have xy axis like so, then the decision boundary would pass right through the origin. And to show that in the diagram, we can create the diagram or the architecture of this single neural network, where we have this is P1, we have P2. So these are the two inputs we have, and each input has a weight associated with it. So this is weight from neuron 1, from input 1 to neuron 1. This is weight for input 2 to neuron 1, and this is the sigma where we sum these up. There's no bias, so we don't write this part right here. So we skip that, and then the output would be n, which goes through the transfer function, and we are going to use again the same transfer function, which is hard lim. That is that if the value is of n is greater than or equal to 0, we say that a is equal to 1. Otherwise, we say that a is equal to 0. That's the negative class. So that we say this is the positive class, we say this is the negative class, and that's exactly what the output of this transfer function is. And so in this case, if you were to name this, we are going to call this as no bias neuron. And again, the equation for this is the same for a is equal to hard lim, and here we have wp, and usually we would have the bias right here, but bias is 0, so we are simply going to skip writing that in there. I will just say that this is wp. Now with that set up, what we are going to do is we'll pick some data points that we would like to classify, and for that we say, let's say we have p is equal to 1 2. That's the first data point, and we have t1, so that's the original target for this one is 1. So we are saying that this particular data point should get classified as a class 1, that is a value of a is equal to 1 when we calculate it. Then for the second data point P2, this has the coordinates -1 2, and the target class here is 0, so that is the negative class. Likewise, we have another data point P3, which has value 0 -1. Again, we say that this belongs to a negative class 0. So these are the three data points, and this time we have previously what we did, or we did guess what the w could be. We drew a line -1.5 1.5, sorry, 1.5 on x, 1.5 on y, and it did work. There we used that to calculate the bias, which was -3, to move that line from the origin. Here there is no bias. So what we'll do is we'll start out with a random value for w, and this time the value for w we are going to choose is going to be 1 0. And to write it in proper notation, here is how we will write it. We'll say that 1, so that is for neuron 1, the weight matrix, we are going to transpose it, because usually we would write that, we would write w as uh, this, right? So we would write w as 2 comma 2 if we when we perform the multiplication, but here we are going to use transpose, and so it really doesn't matter, um, as long as you know how we are trying to perform the dot product. So here we'll say wt 1.0 minus 0.8. What that is saying is, if I were to write w just like that, it would be 1, like so. So we are simply going writing it in the transpose form, keeping in track with the notation we are using in this video. Then bias is 0, so we don't have to worry about it. Let's now go to Desmos and try and plot these. Here we can see that that's our data point. So let's see, here we have our P1, which is this data point right here. Then we have P2, which is this one, P1, P2, P3, and that's our initial weight vector W. And on the left hand side, I've already plugged in all the values so that we save time. And I'll put the links to all of these plots in the description below so you can play around with the plots as well. All right, so let's get started with the way we would calculate the decision boundary, but this time there is one twist and I'll explain what that is. So the very first thing we do, so let's say step one, let's use a different color so we know that this is a different calculation. So step number one, here is what we do. This, we know that this is not a perfect decision boundary, because if we try to plot the decision boundary with those values, we see that it is perpendicular to this weight vector W, which is simply minus this 1 and minus 0.8, and we see that this is a positive class, which is 1 2, as we see here. That gets classified as negative a is equal to 0, and that's not what we need. We need a decision boundary that correctly classifies this 1 2 as 1, class 1 or class positive. So what we do is we get started with the calculating the new W, and to do that we first need to calculate the value of a. So let's try and calculate the value of a with this W that we have. So we write a is equal to hard limb, and here we again use the same uh, setup, which is 1 W transpose P1, and that's the W we have, and P1 is the P1 that we have right here, which is 1 2. So we say hard limb, and in here this is going to be 1.0 minus 0.8, and then P1 is simply 1 2. We do not have any bias, so we just ignore that, and this calculation comes out to hard limb, and this is 1 times 1 minus 0.8 times 2, and so what we get here for hard limb is 1 minus 1.6, and that gets us a value of hard limb 0.6. So that's 0.6 with a negative sign, and so what hard limb tells us is if the value is less than 0, then a becomes just 0, and that is what we get. The point to note here is that the target value for this data point P1, which is T1 that we have here, is 1, and the value that we get here, which is A, is 0, and that is, so there is a difference here, and so to account for the difference, what we are going to do is subtract uh, these two and to get the new value of W. So what we do is uh, we calculate the new W. We calculate the new W, which is new. So 1 W new is equal to 1 W old, and here we use the, and what we do is we subtract the input, subtract or add the input from this based on what we have here. So if we try to get the value of error, error is equal to t minus a, and in this case the error that we have is going to be 1 minus 0, that equals 1. And so what this says is that the sign that we use here is simply going to be plus, and then we add the value of 1 2 to this w to get us a new value of w. And so the sign that we use here would be for p is just going to be a plus. Right? Why? Because if p is equal to 1 and a is equal to 0, then we add the value for p. If it's the other way around, then we subtract the value for p. And so the thinking behind adding the value of p is that uh, hopefully by adding the value of p, we would get this new value of vector w closer to the ideal value of w that will lead us to the best possible decision boundary. And so let's go ahead and calculate our new w. So new w in this case would be w new is equal to the older value that we had, the previous value, which is simply 1 minus 0.8. And recall that here we are not typing the t for transpose, therefore it's like a column. And to this we are going to add the value of p, which is and in this we used value of p1, so we'll use the value of p1. And in the output thus what we get is 1 plus 1 and minus 0.8 plus 2. So this comes out to be 2, and if we subtract 0.8 from 2, we get 1.2. So this is the new w that we have. So next thing what we'll do is in step 2, let's use a different color. Step 2, step number 2, we are going to use this new value of w and again plug those into our transfer function. So hard limb, this time again we have the same weight vector, sorry, the new weight vector, so we can say this is new. So this is essentially referring to the new weight vector, since this is the new one. Dot p2, so we'll try and use a new data point. Previously we used 1, let's now try and use p2. So before we do that, we can come down here and look at how the things would look if we use p2. So that's our new weight vector pointing in that direction. Let's clear this up. And with this new weight vector, we can see that the decision boundary that we are going to calculate now is going to look like this. And so again, it looks like it's not going to be the perfect decision boundary. We still are getting this classified as positive, where it should be negative. It should be a is equal to 0. We already know that, but now we are going to calculate that and see what value of a we get. So we do that by simply plugging in the values for w, the new values. This is transpose, so we convert the column to a row, 2, 1.2, and the value for p, p2 is minus 1, 2. So minus 1, 2. Why we are using that point? As you can see, that is the misclassified point there, and so we use that point, and again we perform the dot product. So we get 2 times minus 1 plus 1.2 times 2, that gets us hard limb 2 minus 1 gets us 2 minus, sorry, 2 times minus 1 gets us minus 2, and plus this is 2 times 4, 2.4, and so what we get is hard limb, and we get a value of minus 0. Plus 0.4, because this is a larger value. So, and if we now try and look at the value of a, it is going to be 1, because if n is greater than or equal to 0, then the value for a becomes 1. So we get a value of 1. So what this is telling us is that the data point P2 is in class 1, and that is exactly what we see in this plot. The decision boundary incorrectly classifies that point as 1. So great. So we are doing good looking at it visually and also calculating it manually. Let's now go ahead and update our W again, and this time the target class for this particular data point, which is T2, was 0. And we can see that up here where we have written, so T2 is 0. And what we need to do now is get the new value of A. So a new value of W. A, what we got was 1. Now to move the decision boundary such that to a W which is closer to ideal W, just because this is uh, 1, the way we can think of about this is we say the error is T minus A, and so we have the value of T is 0, minus of minus of A is, this time it is minus 1, so we have minus 1. So what this tells us, if T is equal to 0 and A is equal to 1, what we do is we subtract the value of P to from the weight vector. So in this case now, if we try and calculate the value for W new, so we say this is W1 and we are using P2, right? So we say W P dot B, sorry, my mistake. Let me just rewrite this part. This is 1 WT, W new is equal to 1 W old plus P, and this time we are not going to do plus, we are going to subtract the value, and so we say minus. Why we are going to subtract? Because that's what we get when we try to get the error, and the idea there is that subtracting P this time would move the decision boundary favorably to accommodate P2 in the correct class, which would be 0. This is negative class. And so we plug in the values, and so what we get here is W, the old W that we have is 2, 1.2, and the value for P is minus 1, 2, and here we said that we need to subtract the value of P, we put a minus there. So what we get here is 2 minus minus 1 becomes plus 1, 1.2 minus 2, and so that gets us 3 and minus 0.8. Uh, so 2 minus, yeah, so minus 0.8. That is the new W that we have, and we are going to now use that value of new W, which is 3 minus 0.8, to continue with the calculation. And let's go to step 3. So in the step 3 we have A is equal to hard limb, and here we have the new value for weight vector, which is 3 minus 0.8, and the value for the uh, data point that we are going to pick this time is 0 minus 1, which is this one, which is the P3 data point. So we take that 0 minus 1, and that gets us hard limb, and this is 3 times 0, which is 0, plus minus 0.8 times minus 0.1, so that essentially is plus 0.8, that is 0.8. And now this time if we say hard limb 0.8, we get a value of 1, because this value n is greater than or equal to 0, and so we get a value of n. Again, this data point, which is I think P3, for this data point P3, the target T3 was 0, but what we get with A is 1, and what that tells us that if we were to correct the values in W, what we need to do is we take the 0 minus 1, so we need to again subtract the value of the the point P3 from the weight matrix to get the new weight matrix that is closer to the value of that gets us the good decision boundary. So we say W1 new is equal to, so the 1W old minus P again, and this time we have the value of W as 0, 3 minus 0.8 minus the value of P3 which is 0 minus 1, and so we plug this in, we get 3 minus 0, then minus 0.8 minus minus 1 becomes plus 1. In the output we get 3 again minus 0. Oh, so this is going to be 1 minus 0.8, that's 0.2, which is with a plus sign. That's the new W we have, and like we'll keep going until we get to the correct weight matrix that we have that gets us a nice decision boundary. So we say we are in step number 4, and in step number 4 we calculate the value of A is equal to hard limb, and here we have 3, 0.2, and then we have the value for P, and this time the value for P that we use would be something different than what we have used before. So let's try and look at this. Let's use the value of 1 2, the value of 1 2, and what we get then in the output is hard limb, and 3 times 1 is 3 plus zero point 0.2 times 2 is 0.4, and this is positive, so we get hard limb which is 3.4, and that's good because now this time we get a value of A which is 1 for this data point which is 1 2, and if we scroll back up, look at that. So for P1 we have a target as 1, so let's write that down here. For P1 the target that we have is 1, and A is also 1. So if we try and calculate the error this time, it is simply 0. And so we if we have reached a point where no longer updates are needed to W, and we found the decision boundary as long as we don't add any new point to this and it gets misclassified. So here if we say W1, so the W that we have, if we were to again try to update the W, it's not going to change because uh, what we have here is the error is so this is T minus A is equal to 0, and so if uh, those are equal, then we simply don't do this, we don't, and so the new W is going to be equal to the old W that we have. And if we now plot that, okay, we can plot a new, that's the W we had from the previous case. We didn't look at that, so that's the one that did some misclassification, and after that the new W that we have which did the correct classification is this one, 3 and 0.2, and so we can try and plot that data point. So let's say that is going to be this one, 3 0.2, sorry, 3 and 0.2. So that's the data point we have, and if we were to convert that to a vector, we say vector starts at the origin 0 0 and goes up to that data point, and we end that to the parenthesis. So that is the weight vector we have. And if we try to create the equation for that, we say 3 times x plus 0.2 times y is equal to 0, and there you go. That is the decision boundary that we found after iterating through various values of W to get to the final decision boundary. And in this case, we do see that both the negative class on the left hand side are classified as with the a is equal to 0, right hand side where the w vector is pointing, that point gets classified as class 1. Awesome. So this time the way we tried to find the decision boundary was starting out with some random value of w, then working through iterations of updating the w by either adding or subtracting the value of p to arrive at the final answer or final w.